Our current era of AI is one of exponential acceleration. Models are scaling into behemoths.
Data centers are stacking endless rows of GPUs while burning ever more power.
AI labs are locked in a race for compute, energy, and capital. The sheer momentum of the whole industry is palpable, and yet, the story still feels incomplete. Brute forcing today's digital, deterministic paradigm
To unfathomable scales simply cannot be the endgame.
For artificial intelligence to fulfill its full promise, we need a non-incremental gain in the density of intelligence. Our very existence, that of biological general intelligence, is proof that there exists a better way forward. One that is far removed from digital computation, one that harnesses the inherent randomness in nature, and one that is far more parameter, data, and power efficient. At Extropic, we took guidance from nature to design such a new form of computing from the electrons up. By leaving conventional bits behind and instead embracing pbits, we carved a new path that promises more intelligence per watt, per square millimeter, and per second. As we make our way along this path, today, we have several updates to share with you, which span our entire thermodynamic computing stack. So join us on our journey to build the ultimate substrate for intelligence. Last fall, we announced X0, our first ever thermodynamic chip. With X0, we demonstrated novel probabilistic primitives in silicon that serve as our building blocks for our current and future chips. We also shipped our first desktop devices featuring this chip, the XTR0 experimental testing platform, which is now in the hands of early adopters. Along with this test kit, we shipped our first software, Thermal, a library for thermodynamic hypergraphical models that lets developers experiment with thermoprogramming close to the metal. With X0, we took thermodynamic computing from 0 to 1. Now, it's time to turn it up from 1 to 1 billion.
Before we get to the hardware though, let us start with some updates on our thermodynamic software stack. We heard you after our last launch. Cool alien computer, but how am I supposed to program this thing?
So we went out and built new layers of our stack, inspired by the deep learning frameworks you know and love, to make thermodynamic programming feel less alien. Deep learning conquered software because one could write parameterized programs and find the best ones with gradient descent. Now we're extending that same philosophy to the programming of stochastic devices. Today, we're excited to release Torx, our new open source framework for general stochastic differentiable programming, going beyond strictly thermodynamic programs. For the first time, you can build stochastic programs and train them with gradient descent, just like neural networks. You can apply them to simulations of nature, sampling, machine learning, and much more. In classical differentiable programming, you arrange modular, parameterized functions into a directed acyclic graph. Torx lets you build the same kind of graphs, but where the nodes are stochastic transition kernels. They're distributions over functions, wired together in series and parallel. The result is modular probabilistic programs with depth in a natural flow, trainable end-to-end with your favorite optimizer. To put simply, Torx is to thermal what PyTorch is to CUDA. Torx is hardware agnostic and can run on stochastic processing units of all kinds, from our very own XTR0 today to our next chip, Z1 and beyond. The white paper we're releasing today walks through a wide array of examples to get you started. Explore the docs, code, and examples at torx.ai. Alongside Torx, we're releasing a white paper on Thermalizers, our upcoming thermodynamic compilation library. Thermalizers lets you compile arbitrary Torx programs onto thermodynamic devices like Z1. It bridges Torx and thermal, thus completing our full thermodynamic programming stack.
It works by variationally compiling each stochastic transition kernel in your program into a hardware-aware, energy-based models over input and output variables. The result is a directed graph of thermal models that maps directly onto our thermodynamic hardware fabric, enabling stochastic program execution via in-memory pipeline parallel sampling.
Now, for any application, anyone can take a general, high-level stochastic program and readily map it onto thermodynamic hardware without having to manage low-level device details.
For the right workloads, this can deliver up to 10,000x greater energy efficiency than GPUs.
You can read more about Thermalizers in our recent blog post. You can go check out the white paper on Archive, and you can watch our GitHub for the open source library release in the coming weeks. The generative AI era is one dominated by probabilistic software, and people serious about probabilistic software should be building it for probabilistic hardware. At Extropic, we firmly believe in the power of co-design, as only what evolves together ultimately fits together.
As such, our probabilistic software frameworks announced today were explicitly designed with with our next generation of probabilistic hardware in mind. And so today, we can finally share more about our next generation of hardware. At its core is our newest chip, Z1. Z1 is comprised of over 250,000 pbits arranged in a sparse graph. Each of these pbits has 60 neighbor connectivity while supporting a sampling rate of over 50 megahertz. Z1 fits 269,000 pbits on a chip that consumes less than 1 watt while measuring less than 12 millimeters per side.
We plan to make Z1 systems available in 2 form factors. First, an edge-ready thermo compute stick with over 500,000 pbits in an M.2 form factor, enabling low-power applications at the edge, such as next-generation augmented reality and robotics.
For the heaviest probabilistic workloads, we are also building Z1 accelerator cards. These thermodynamic accelerator cards pack over 4 million pbits each, enabling scaled-up thermodynamic workloads for the very first time. They come in a standard PCIe card form factor for workstations and servers, enabling them to be slotted right alongside your favorite other accelerators. This will enable the exploration of AI workloads on heterogeneous thermoclassical compute hardware.
Next year, we plan to build the world's very first billion pbit cluster with these cards. This will enable the discovery of novel model architectures that can run natively on our thermodynamic hardware at scale, bringing us one step closer to artificial general thermodynamic intelligence.
Z1 is finally taped out.
The Z1 cards and sticks slated to be available for early access in 2027. The world urgently needs more energy-efficient AI hardware, and to address this, we're building up our thermodynamic intelligence stack from the ground up with haste. Today, we're open sourcing our software tools in order to catalyze collaboration with the broader AI community and propel forward the next era of intelligence. To facilitate this, we're releasing an open access API to run Torx and thermal programs on high-performance GPU simulators, enabling you and your favorite agents to iterate faster on thermo AI research. Over time, we plan on providing higher performance simulators through this API, more tools for agentic accelerated research, and even access to our first Z1 clusters. Now is the time to join our rebellion. We are in the foothills of thermodynamic general intelligence, and we want you to come climb this next peak with us.